Alright, in this section here we're going to be talking about concavity and points of inflection. So we're still analyzing the graphs of these functions here. This particular one we're talking about is x squared plus 1. So this is the graph here of x squared plus 1. And we talked about earlier that to find the minimum on the graph, and that would be about right here. Okay. In this particular section here, we're going to be talking about concavity. And I'm just going to tell you here that as you can see the graph, it's concave up. Okay, so I think after I work a few examples, you'll be able to look at a graph and tell whether it's concave up or not. But pretend that this is like a cup and it holds water. Okay, pretend it's a cup and it holds water. So if it holds water, we can say then that it's concave up. Alright, well, let's figure out how to determine this, and so let's go to the whiteboard. Alright, so first thing I'm going to do, of course, is let's write out that function f of x is equal to, and that was x squared plus 1. Okay, so to find the minimal point on the graph, we took the derivative, the first derivative, we set it equal to 0, and we got our critical numbers, and we plugged those critical numbers back into our function to actually find the point on that graph. And I'll just kind of sketch the graph out right here, which was, right, this particular graph, the minimal points here. But to find the actual concavity, what we want to do, and the inflection points, what we're going to want to do here is we want to take the second derivative. So we're going to take the derivative. So the derivative of 2x is just 2. And then what you do is you set this equal to 0 and solve for x. Well, there are no critical numbers here. In other words, there's not a number that we can plug into this to get 0. Okay? So no matter what number we plug in, f double prime, for example, if we were to plug in negative 10 into this, we still get 2 out. And 2 is a positive number. Okay, so if you looked at this as like on a number line, no matter what number we picked on the number line and we plugged into our function, we always get a positive number out. So no matter what it is, we're always going to get a positive number no matter what number we choose on the number line. And we could say then that this graph is concave up. Now you notice this line I'm using here, it's it's not a straight line where I used straight lines to determine if the graph was increasing or decreasing. I use these concave type lines here to determine whether the graph is concave up or down. So in this particular case, okay, we don't have any inflection points. But we can say that the graph is concave up, and I'm just going to label it as CU here, is concave up from negative infinity to positive infinity. Okay, well, let's look at another one. So in this one here that I'm about to write up, I don't know, we'll call the function r. How's that? So this is going to have all kinds of stuff. We got x cubed minus 6x squared plus 12x. So the first thing I'm going to do is I'm going to take the first derivative, r prime of x, gives us 3x squared minus 12x, and then plus 12. And then I'm going to go ahead and take the second derivative. Wow, that's an r, doesn't look anything like that one, but whatever. So we end up with 6x minus 12. We're taking the second derivative, we're setting it equal to 0, and we're going to get these critical numbers. Alright, we set it equal to 0 and then find the solution to this equation here, which is going to end up being 2. So, alright, this is the solution. Okay, and x is 2, we plug that in, we get 12, and 12 minus 12 is 0. Alright, so that's going to be our key number right there. So to find the inflection point, I'm going to take okay, so this is the actual point on the graph here. So we take the original function r of x and we plug 2 directly into it. So that's going to end up being two cubed minus 6 times 2 squared plus 12 times 2, and after doing the arithmetic here, you should get 8. So the inflection point, and I'm just going to label it with IP, inflection point, and it's a point, so that means we got an ordered pair here, so that'd be 2 comma 8. Okay, and I'll bring the graph up here in just a minute and we'll see what we're looking at here on that. Now to find where the function's concave up or concave down, what we're going to do now is I'm going to draw a number line. So this is just like how we determined if a graph was increasing or decreasing. I'm going to put 2 on the number line. Okay, and then I'm going to pick some test points. And we'll pick 0. 0 is always a good one. And how about 3? And so what we're going to do now is we're going to take these test points and plug them into the second derivative, and it'll tell us whether the graph is positive or negative. And that's all we're really concerned about, is the sign out once again. So if I were to take 0, take 0 here, and plug it directly in, doesn't matter which one we're looking at, plug it in right here, you get 6 times 0 is 0, and so you get a negative out. So that's going to be negative, and that means that we're going to have concavity. So I do it like this, just draw me a line so we know it's concave down from negative infinity up to 2. And then I plug 3 in, and 6 times 3 is 18. 18 minus 12 is going to be a positive number. Okay, and then we say that the graph is concave up from 2 to infinity. And we'll write that out right here. So concave down, I just label it C and D here. We got from negative infinity to 2. And it's concave up from 2 to infinity. Okay, so we found our inflection point and we found our concavity. Now let's actually take a look at the graph. Okay, so here's a graph of that function, and here's about where 2 is located. Okay, so as you can see, remember I said that concave up in the last problem, you can think of it as like holding water, right? And then of course this part of the graph is concave down up into 2, and then concave up. And where this concavity changes is what's known as the inflection point, and that was at 2, 8. And so we're looking at our coordinates over here, and I'm trying to get close, but as you can see there, anyway, it's at 2, 8 is where the actual inflection point occurs, and that is where our concavity changes. Okay, where the concavity actually changes. We can, let's see, oh, that's zooming out. Let's zoom in real quick here, maybe get a closer look at what's going on. As you can see, the y-axis is really zoomed out more than the x-axis is. That's the reason the 8 looks like it's lying on the x-axis, but when x is equal to 2. But okay, so pretty easy. We're going to work lots of these problems, so you'll get the hang of it. Okay, so we're finding concavity and points of inflection. And we're just going through and learning this stuff by me working examples out and you studying the patterns. Okay, so we have 1/4 x to the 4th. minus 2x squared. You know, that's how I found math to be much easier to learn, and that's just watching somebody work examples out. And I always hated when the instructor talked about the theory all class and then gave us homework on the problems, and we had to try to figure out how to work them out, even though I guess there's nothing wrong with trying to stretch your brain, but it seemed like I never did get enough examples worked out in class. Okay, so what we want to do here is want to take the first derivative. Let's find the first derivative. And let's see, taking the 4 out front, 1/4 times 4 is 1. And so you're left with x to the third minus, and then bring the 2 out front, so that's 4x. So at this point in the game, I'm hoping that you know how to take some simple derivatives like those. Now what we want to get to, though, is the second derivative, because that's going to indicate, give us our concavity and points of inflection. At least most of the time it will. Sometimes we can't do that, though. Use the second derivative, and we got to go back to the first derivative, but I don't know if we'll talk about that or not. But anyway, let's see, that's a 2 there, and then minus 4. Okay, so we want to do is take that second derivative, set it equal to 0, and find the solutions to this equation. And so that's going to end up being 4 thirds square root plus or minus. Okay, solving for x in this equation, this is what we should get. And of course we can simplify this down to 2 over the square root of 3. Right, square root of 4 is 2, and then you have square root of 3. And we could get this radical out of the denominator, but I think I'll just leave it there. What the heck. Okay, so here's two possible points of inflection where x is equal to plus or minus 2 over the square root of 3. At least that's our x values. We'd have to find our y by plugging those directly back in to the original function. And why don't we just go ahead and do that and get that out of the way right now. So f of 2 over the square root of 3 is equal to, so we're plugging these back into the original. And that's to the 4th power minus 2 times 2 over the square root of 3, and that's squared. Now I'm not going to go through all the arithmetic here and showing you how to figure out how to get all this. I'm just going to write it out right here. So that should be negative 20 over 9. So hopefully you can work all this out and get negative 20 over 9. Okay. Now if I were to plug in a negative in here, if this were a negative right here, because we got two solutions, we got a positive one and a negative one, because this is raised to the 4th power, it's not going to make any difference. Our answer is still going to be the same, negative 20 over 9, if we were to plug in the negative 2 over square roots of 3. And that is because this is raised to the 4th power and that's squared, and right, take a negative raised to the 4th power, you get a positive, and a negative squared is also positive, so that's not going to change any at all, right? So I'm going to say that our points of inflection are going to be 2 over the square root of 3, comma, negative 20 over 9, and negative 2 over the square root of 3, comma, negative 20 over 9. Okay, so those are our points of inflection right there. Now what we want to do is find our concavity. Okay, so now we're going to draw a number line. And on this number line, we're going to plot these guys right here. 2 over the square root of 3 and negative 2 over the square root of 3. So let's do that. So we'll put negative 2 over the square root of 3 here, and how about 2 over the square root of 3 here. Then we want to mark where our test points we're going to use. We're going to always use 0 if we can. And then the question is, you know, how far over do I need to go? This is 1.15. Whoa, Nelly, I forgot to put the square root down here. I was about to say 2/3 is not 1.15. So this is negative, approximately negative 1.15. So let's go over to negative 2 here. And then we'll go over to positive 2 on this side. Alright, so we want to take negative 2 and we want to plug that into the second derivative. And of course, all we're concerned about is if it's positive or negative. So let me rewrite the second derivative right here. So f double prime of x is equal to 3x squared minus 4. Okay, so all we're concerned about is if it's negative or positive. So if I take negative 2 and I plug it directly in, we get negative 2 squared is 4. 3 times 4 is 12, and 12 is greater than, well, I'd just say 12 minus 4 is a positive number. How's that? And so that's positive, so we know that this is going to be concave upward. Okay, from negative infinity to negative 2 over the square root of 3. Then we plug 0 in, and we get a negative number. So we know that that's going to be concave down. Then we take 2 and plug it in, and of course that's going to be positive also. Right, 2 squared, you know, this would be the same thing as plugging negative 2 in. So that's going to be concave up. So now we got our concavity, so we can say concave up from negative infinity up to negative 2 over the square root of 3. Now we also have another one. We can say union or whatever, comma. Put a comma there. I've just put a union because we're joining both these sets together. And then this would be from 2 over the square root of 3 to infinity. Okay, so that's where it's concave up. And then concave down is from negative 2, right, over square root of 3, comma, 2 over square root of 3. Okay. I guess, I don't know, did we look at the graph yet? Let's take a look at the graph. Okay, so we're looking at the graph of that last function that we found the concavity for, if you can remember some of those numbers. Anyway, this nice feature here that Google now offers, I just typed this into the Google search box. Actually, I'm using Google Chrome, and I guess I need to mention this. And I'm actually typing this in up at the address bar where it says, you know, where you type in google.com. Anyway, I'm typing this in and this comes up. Sometimes when I type this into the Google search engine, I don't get this graph to come up, so I don't know what reasoning behind all that is. But anyway, so we can look at the graph here, and hopefully you remembered some of those numbers. As you can see here, the graph has a local minimum around in this area right here, and then we got a maximum here, relative max, and I should say relative, and then relative min here. I guess depending on the interval that we're on, if we're on the interval from negative infinity to positive infinity, you know, these are considered really global mins here, and this would be considered to be a local maximum. You could say relative maximum, right in here. So anyway, where are we at here? Oh, we're talking about concavity. And the point of inflection, so remember that's where the concavity changes. So as you can see, remember I say concave up, it holds water. And then concave down, right, it doesn't hold water. Concave up, it holds water. Okay, so somewhere in here's a magic point, and that point we call the inflection point, where the concavity changes from being concave up to concave down. Okay, and we found that inflection point, and that was at the it was 2, let's see, negative 2 over the square root of 3 and negative 20 over 9, which was the y value. So that's somewhere about right in here. Okay, somewhere in this area right here is going to be the concavity, or the inflection points, I mean. Um, okay, so I'm just kind of guessing it here, from about right here and then up, right, it's concave up, and then you can see concave down, right, and then concave up right here. Okay, well, that's enough about this problem. Let's move on and work some more. Alright, well, we're just going to go straight to the graph on this next problem here. This is the function here that we're going to be working with. This is x times x plus 3 raised to the half, which is, I'm going to have it written out initially as the square root of x plus 3. Anyway, so this is the graph down here. Nice, interesting graph. And if you notice, the graph stops right here, and there is no more graph. And that is because the domain of this function up here, you plug anything less than negative 3 into this thing, you get a negative under the square root. And of course, then we get into the imaginary stuff. But anyway, so the domain of this function is everything greater than or equal to negative 3. Okay? So that means we're looking at the graph from negative 3 onward in this direction. And you can clearly see by this graph that it's concave up, right? And it's going to be concave up from negative 3 to infinity. And we're probably not going to find any inflection points because the concavity of the graph is not changing. We can zoom out some more on this graph and take a look at it, and as you can see here. Okay, so let's get to the whiteboard and figure this out. Okay, so I'm going to say that there's going to be a lot of algebra to deal with in this problem. I'm not going to get caught up in a lot of the algebra. You know, this is not supposed to be an algebra class, but it's supposed to be a calculus class and learning some techniques in calculus. Now, we're initially given this right here. And of course, we need to go ahead and get this out of radical form and write it in exponential form. Alright, so now we got it into exponential form. It's time to... I don't know what's going on here all of a sudden. Board's acting funny. Okay. Whoop, f prime. So we take the derivative of x, which is just 1, and we rewrite plus, take the, rewrite the x. I'm going to take this half, bring it out front, times x plus 3, and subtract 1 from the exponent, so that gives us a negative a half. And of course we'd take the derivative of what's in parentheses and bring it out, but the derivative of x plus 3 is just 1. Okay, I think what I'm going to do now is I'm going to do a little factoring. This way it makes things a whole lot easier when we take the second derivative. So this is kind of an important thing that you got to do in calculus, and that's factor. And especially when you get to this section here on relative extremas and so forth. But I'm going to factor, okay, so we got x plus 3, we have an x plus 3 here, raise to the negative, raise to the half. You always pull the one out that has the smallest exponent. And that's going to be the one that we factor out, the x plus 3 to the negative a half. Okay? And we end up with x plus 3 here. Now think about it. This x plus 3, if I put parentheses around this, it would be raised to the 1 power. And when you were to multiply this back inside, you add exponents. So 1 minus a half gives us a half. Okay? Plus, and then of course we pulled this whole thing out, and we're left with x over 2. Now we want to go ahead and simplify this down here as much as we can, and we end up with and you know what, I'm going to go ahead and rewrite this. This is a negative a half, so I'm going to take this down into the denominator while I'm at it. So we have like terms here, x and then a half, or x over 2, so we can rewrite that as 3 halves x plus 3, and that's going to be over x plus 3 raised to the half. Good enough. And this is f prime of x still we're working on. And we want to get to f double prime of x. So that means we've got to take the derivative again. That's okay, we can do that. So f double prime of x is equal to, so we're going to use the quotient rule, taking the derivative of the numerator, and we're just going to be left with, it looks like, excuse me, the derivative of the numerator is just 3 halves times the denominator, which is x plus 3 raised to the half, and then minus the numerator, 3 halves x plus 3, and then the derivative of the denominator. So we take the half out front, rewrite x plus 3, and we subtract 1 from this exponent. That gives us a negative half, and of course if you took the derivative of the inside, you bring it out, it's just 1. And then of course this is all over x plus 3, and we square the bottom, so that means we multiply 2 times a half, which is just 1. So we're just left with x plus 3. Okay. Okay, so let's do some factoring and canceling some stuff out here. We got an x plus 3 raised to the half, and x plus 3 raised to the negative half, so this is going to be the one here that I pull out. We have a half, we have 3 halves, so I'm also going to pull out a half. Okay, since there's a half in here and a half over there and here over there and over there. Okay, so let's try to, man, it's hard to be neat on here. You know, writing on these tablets is a difficult thing to do when you're trying to be neat. So I'm going to pull a half out. And I said that I was going to pull an x plus 3 and to the negative half out. And where are we at here? Okay, I'm going to start a bracket here instead of a parentheses. So we're going to have a 3 times x plus 3 and a minus 3 halves x plus 3. And of course I pulled this half out, and this x plus 3 raised to the negative half, I pulled that out also. Okay, and that is all over. I'll be glad when I get done with this problem. X plus 3. Alright, and I don't know, I'm putting parentheses around it, I don't know why. Okay, simplify what's in the brackets here. We can take this down into the bottom, and that's going to become a positive half. So we end up with f double prime of x x is equal to, I'm going to go ahead and distribute this stuff across. This is going to be 3x plus 9 minus 3/2 x and then minus 3. Good enough. I'm going to go ahead and take this 2. I'm going to bring that down into the denominator. X plus 3 raised to the 3/2. And the reason for that is because I'm taking this down into the denominator, so this would be x plus 3 raised to the half. Since both of our bases are the same, you just add exponents, right? A half plus 1 gives us 3/2. Okay, just simplifying. Okay, I've run out of canvas. I'm going to have to jump to another screen now. Alright. Okay, so I'm going to have to rewrite this stuff here. F double prime of x is equal to 3x plus 9 minus 3/2 x minus 3, and of course we're going to have to simplify this down, so I'm trying to keep from skipping any steps here, even though at times I do skip steps, but the steps I'm skipping is supposed to be the easy stuff you're supposed to know how to do, even though they are canceling algebra in the 8th grade all over the country. Terrible. Okay, I don't want to get off on that right now. Let's simplify this down. We got 3, with some like terms here, 3 minus 3/2 x, and so we're left with 3/2 x. We got 9 minus 3, and that's going to be a plus 6 over, my goodness, takes forever to do this stuff. Alright. But you learn a few of the rules and you can do this stuff all day long. Okay, now it's time to set the numerator equal to 0, find out what's going on in the denominator here. Okay, so now what we want to do is set the numerator equal to 0. And solve this equation, which a third grader should be able to do at this point. I don't know. I'm down on the education right now, hearing too much bad stuff on the news lately about how kids don't need to learn algebra anymore. Let's see, what do we got going on here? We want to solve for x in this problem, and if we were to plug in, never mind, let's just do it the old-fashioned way. Then we want to multiply both sides by 2/3, the reciprocal of this guy here. And so we have times 2/3. And of course, x is going to end up being equal to, okay, that can't be, let's see, well, we get x is -4, but something's going on with that, because if -4 is not in our domain of the original function, okay, so that doesn't work, right? This second derivative thing is not working for finding concavity or points of inflection or any of that. As you can see, it fails there. Right. Anyway, so not in the domain of the original function. Remember, it was x plus 3. It was x and then x plus 3, right, was the original function here, f, and you can't plug -4 into this guy right here. So there you go. We need to go back to the first derivative. And that means taking the first derivative and going through the same things we've gone through to find the relative extrema in some previous videos. But okay, so that's really what you need to do. You need to go back to the first derivative and then do the number line and look where the graph is decreasing and then increasing, and you can tell from there where it's concave up. So let's just quickly go back and look at the graph. So this was the graph of our function here, and right, so the domain you can see here, graph starts here. But anyway, you can see, so you'll have a minimum somewhere in here, right? Looks like about -2, but I can't guarantee that. And you can see that it's concave up from -3, okay, all the way to positive infinity, right? So you're going to have decreasing and then increasing, as you can see here, and you can determine if it's concave up that way. Alright, I think that's enough of this problem. I have had enough of this problem, and I think that's it. That's all I'm going to have on concavity and inflection points. If you want any more problems work, send them to me on YouTube in the comment section, and I'll try to work them out. Thanks.